All right, so today we're taking a deep dive into, well, deep space, black holes.
Quite literally a deep dive.
Right. We had a listener question about their shape, specifically why they're so perfectly round.
It's one of those things you don't think about, right? But it's a really good question.
It's deceptively simple, but it gets at some really fundamental physics.
Absolutely. It takes us right to the edge of what we understand about gravity, space-time, the works.
Okay, so I have a decent handle on what a black hole is, generally speaking. Could, collapsed star, gravity's gone insane, not even light can
A
escape.
classic description, yeah.
But before we get into the whole roundness thing, could you maybe give us a little Black Hole 101 refresher, just to make sure we're all on the same page?
Sure thing. So picture this. You've got a star way bigger than our sun, many times more massive, and now imagine squeezing all that stuff down, 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 until it's smaller than a pinhead.
That is one dense pinhead.
That's basically a black hole. You've got all that mass concentrated into this incredibly tiny point. We call that point a singularity.
And that's where things get really, really weird. Right, like what actually happens at the singularity? Does time even exist there?
Okay, so those are the million-dollar questions, and honestly, we don't have all the answers. Our current understanding of physics, it just stops working properly at that point.
It's like the universe's here be dragon sign.
Pretty much, but we do know that surrounding every singularity, there's a boundary. We call this the event horizon, and that's where things get really interesting and inescapable.
Okay, so the event horizon, that's like the ultimate point of no return. It's not a physical surface, right? It's more like this invisible barrier.
Exactly. It's the point where gravity is so strong that nothing, not even light, can escape. Cross that line, you are not coming back.
And that's why we can't actually see a black hole directly.
Right. Trying to see a black hole is like trying to look at a shadow that devours all light.
That's a good one. So we have to get creative. We can only observe them indirectly.
Exactly. We look for their effects on the stuff around them, like how their gravity affects the orbits of nearby stars, or how it bends the path of light that passes too close.
So it's like cosmic detective work.
That's a great way to put it. We're looking for the fingerprints, the clues, the distortions that tell us, hey, there's something massive lurking here.
Okay, so we've got these incredibly dense objects warping space-time around them. But here's my question. Lots of things in space, they're not perfectly round, right?
Right.
I mean, planets bulge at the equator, stars can have weird shapes. So what is it about black holes that makes them the ultimate cosmic marbles?
It all comes down to the sheer mind-boggling strength of gravity in a black hole. It's so powerful that it overpowers everything else, literally flattening out any bumps or irregularities.
So it's like the universe's most extreme iron, just smoothing everything into this perfect sphere.
I like that. Think of it this way. Imagine you have a big lump of clay, right? If you squeeze it from all sides with enough force, what shape does it naturally want to form?
A sphere. Makes sense, it's the most symmetrical shape.
Exactly, and that's what gravity's doing in a black hole. It's squeezing, or rather pulling, everything inwards with such unimaginable force. A sphere becomes the only shape that really works.
It's the most efficient way to pack all that mass and energy into the smallest space possible.
Exactly. Like packing a suitcase, you gotta get it all in there.
Okay, so gravity is this cosmic sculptor, always working toward that perfect form. But wait a minute. Don't some black holes spin?
Ah, you're thinking of Kerr black holes.
Kerr black holes. That sounds intense. So what happens then? Does a spinning black hole become like, I don't know, a cosmic frisbee or something?
Not quite a frisbee, but it does get wild. Because when a black hole spins, it doesn't just drag matter along, it actually drags space-time itself. We call it frame dragging.
Frame dragging. Okay, now you're just messing with me.
It sounds like something out of Star Trek, right? But it's a real phenomenon.
So what space-time itself is getting pulled along for the ride? I'm not sure I even understand what that looks like.
It's definitely a head-scratcher. Imagine a black hole like a whirlpool. The water closest to the center spins the fastest. Yeah, it's kind of like that with the rotating black hole. Space-time itself gets pulled along, and that can cause the black hole to bulge a tiny bit at its equator.
So instead of a perfect sphere, it's more like a slightly squashed sphere.
Exactly. But even with that spin, the gravitational pull is so strong that it maintains a nearly perfect round shape. Think about how much gravity it takes to literally drag space-time around.
Okay, my brain is officially fried. So we've talked about gravity's incredible pull.
Yeah.
But to really grasp WHY this sphere shape is so important, we need to bring in the big guns, right? Einstein and his whole warped space-time thing.
We're talking about Einstein's theory of general relativity, and you're right, it's essential for understanding this. See, Einstein showed us that mass warps the fabric of space-time itself.
Right, like that classic bowling ball on a trampoline analogy. The heavier the object, the more it distorts the fabric, right? Making this kind of like a gravitational dip that other things fall into.
That's the idea. Now, with a black hole, imagine a bowling ball so heavy it stretches the trampoline practically infinitely down. That's the kind of extreme gravity we're dealing with.
Okay, so planets and stars, they're like tennis balls on this trampoline.
Yeah.
Black holes are like the mother of all bowling balls.
You got it. And here's the key, the sphere, you see. That's the shape that minimizes the energy in that warped region around the black hole. It's the most stable configuration in all that distorted space-time.
So black holes are like cosmic energy savers. They're all about efficiency.
In a way, yes. It's all about equilibrium, finding that lowest energy state. Think of it like a soap bubble. You can distort it, you can poke it, blow on it, but it always wants to go back to that perfect round shape, right?
Yeah, because that's its most stable state.
Exactly. It's the lowest energy configuration. And it's the same principle with black holes, with their warped space-time bubbles. They want that spherical shape.
So black holes are like the universe's perfectionists, always going for that ideal form. It's like the cosmos has an aesthetic preference or something. But okay, let's say, a black hole gets into a little cosmic fender bender, like it bumps into another black hole, or maybe a giant star gets too close. Could that mess with its perfect shape?
Well, it's a wild universe out there. Collisions definitely happen.
Right.
And yeah, those interactions, they can get pretty intense. When two black holes collide, for example, and we know this happens, they don't just bounce off each other.
What happens?
They merge.
Whoa.
And it's this incredibly energetic event. It sends ripples through space-time, what we call gravitational waves.
Gravitational waves? See, now that's a whole other deep dive. We'll have to add that to the list.
Mm-hmm.
But back to these colliding black holes. What happens to their shape during this whole cosmic mosh pit? Do they just turn into some kind of cosmic blob?
During that merger, yeah, the shape of that newly forming black hole, it can get distorted. It's like taking two soap bubbles and smushing them together. You'll get this weird wobbly shape for a little bit.
So even black holes can't escape a little awkward phase now and then.
But it doesn't last, right? They don't just stay as these cosmic blobs forever.
Exactly. Just like that soap bubble analogy, even if a black hole gets, stretched or dented temporarily, that intense gravity, it's always there, working in the background, pulling it back towards that stable spherical form.
It's like this constant battle between chaos and order.
That's a great way to put it. Disruption and equilibrium.
Okay, so we've got gravity playing cosmic sculptor, always smoothing things out. But there's another layer to this, right? You mentioned something earlier about quantum mechanics. And I always feel like when someone says quantum, things are about to get a little weird.
Quantum mechanics always adds a fun twist. So at the quantum level, things get a little fuzzy. It's like the universe is a little grainy. And there's this inherent fuzziness, this constant hum of what we call quantum fluctuations. Basically, even in a vacuum, even in the emptiest space you can imagine, there are these tiny temporary changes in energy popping in and out of existence. So like the universe is never truly off. There are always these little energy blips happening everywhere, even at the tiniest level.
Exactly. It's like the universe is constantly shimmering, just buzzing with these quantum fluctuations. And here's the thing. These fluctuations, tiny as they are, they could theoretically affect the shape of a black hole.
Wait, really? So even these perfectly smooth, spherical black holes we've been talking about, they might actually have like microscopic imperfections because of quantum mechanics.
That's the idea. We're talking incredibly small scales here, smaller than anything we can actually observe right now. Imagine the smoothest, roundest marble you can think of, and then imagine imperfections on that marble 1 billion times smaller than an atom.
Okay, so we're not talking about black holes suddenly looking like, lumpy potatoes or...
Oh no, nothing that dramatic. It's more of a theoretical possibility right now than something we can actually see.
But still, it makes you wonder, if even black holes aren't immune to the fuzziness of the quantum world, what does that say about, the nature of reality itself?
Now you're asking the big questions. That's one of the things that keeps physicists up at night. It's like we're looking at two different pictures of the universe. On the one hand, you have this smooth, continuous picture from general relativity. And on the other, you have this grainy, uncertain picture from quantum mechanics. And we're still trying to figure out how to fit those two pictures together perfectly.
It's like trying to solve a jigsaw puzzle where half the pieces are from a completely different puzzle.
That's a great analogy. But Okay, let's say, hypothetically, we could somehow control these quantum fluctuations. Could we, manipulate a black hole's shape, stretch it out, mold it into something else? Could we turn a sphere into, a cube or a pyramid? That's a question that really pushes the boundaries of what we know. Right now, everything we understand about physics screams sphere. That's the shape for black holes. It's the most stable, the most energy efficient. But there are some theoretical physicists who love to play with these what-if scenarios.
They're the cosmic rule breakers. So what are they saying? What kind of crazy shapes do these theoretical black holes come in?
Well, some physicists have explored mathematical models where black holes, they could exist in universes with different laws of physics, different dimensions than our own.
Okay, different dimensions. Now we're getting really out there.
Right. And in these hypothetical universes, black holes, they might not be limited to being simple spheres. Some models suggest they could be ring-shaped, cylindrical, or even have more complex geometries that are hard to even wrap your head around.
Okay, black holes shaped like donuts. Now that's something I've got to see to believe. But seriously, is there any chance that these exotic black holes could actually exist? Or are we talking purely hypothetical, mathematical curiosities here?
As of now, they're purely theoretical. But, black holes themselves were once considered purely theoretical objects. That is, until we started observing their effects on the universe around them.
That's true. What seemed like pure science fiction a few decades ago is now just another part of our understanding of the cosmos. So who knows what the future holds?
Exactly. The universe is full of surprises. And honestly, the more we learn about black holes, the more we realize how much we don't know.
It's kind of a humbling thought, isn't it? Even something as seemingly simple as the shape of a black hole can lead us down these incredible paths, challenging everything we thought we knew about reality.
It really speaks to the power of asking questions, of never taking anything for granted.
It really is amazing, isn't it, how even when we're talking about these incredibly massive, powerful objects, this kind of elegance shines through.
It's true. There's a beauty in that simplicity.
It makes you wonder, though, if even these chaotic objects, these black holes that gobble up light and warp space-time, if even they are drawn towards this perfect, symmetrical form, what does that say about the universe itself? Is everything searching for that balance?
That's a deep question. And honestly, it's one we're still grappling with, but it does make you think, could this principle of symmetry, this drive towards equilibrium, could it extend beyond just black holes? Could it be, woven into the very fabric of reality?
Whoa, that's a pretty mind-blowing thought. That maybe it's not just black holes, right? Maybe it's everything, from the smallest particles to the largest structures in the universe, all being guided by this cosmic dance of balance.
It's a beautiful idea, and it really highlights how interconnected everything is. When we study black holes, we're not just studying these distant, exotic objects. We're studying the fundamental laws that govern our reality, the stage on which the entire cosmic drama unfolds.
I like that, the cosmic stage. Well, I think that's a pretty epic note to wrap up on. So, to our listeners out there, next time you see a picture of a black hole, that inky black circle against the stars, remember, it's not just an empty void, it's a sphere of immense density and gravity, warping the fabric of space-time around it, and maybe, just maybe, holding the keys to some of the universe's biggest secrets.
And who knows, maybe someday we'll have the technology to see even more, to glimpse those theoretical black holes, the ones with those crazy shapes, the donuts and the whatnots.
Imagine that, black hole donuts. We've come a long way from wondering why they're round.
That's what makes it so exciting. There's always more to discover. Never stop questioning, never stop exploring.
Words to live by. That's a wrap on this deep dive into the heart of black holes. Catch you next time for another cosmic adventure.